Okay, in today's lecture, we are going to talk about the measurement systems. Okay, just a quick idea that what are the different components of a measurement system, because this is how we go to the measurements that we are going to talk about during the course of this particular course. So the measurement systems are basically, for example, since we are dealing with fluid mechanics, let's say the fluid mechanics, an experiment is performed. Basically, we want to measure the flow, right? Thus, in any fluid mechanic experiment, one may identify three distinct systems. They are dealing with a fluid mechanics, experiment. So you are dealing with three distinct systems. All right. Okay. So first one is a physical system. All right. So this consists of the flowing fluids, the apparatus, the test models, and the related objects. Right. Okay. So it includes the fluidic system. Okay. You see the test models, for example, and of course have any other related apparatus. Okay. Then of course you have the measurement system. So that's what you are going to do, the measurement system. Okay, this measurement systems are basically consists of your sensors, your electronics, whatever the sensors may be, your data acquisition or DAQ, as we call it, the processing devices and software, image analysis, if you have analysis, etc. Okay. So, and of course, then you have the experimenter, which may be the persons who basically his job is to interpret the data, okay, and also execute the measurements. So this is a very, more details about this you can find in the measurement in fluid dynamics. This is a Cambridge University Press book, which is highly recommended. So the measurement system. So let us look at the measurement system in particular. So the measurement system, okay, this has got one or more inputs and one or more outputs. Okay? So it can have one or more inputs and one or more outputs. All right. So output of each component may represent an input to another component. This can also happen. So each input or output corresponds to a physical property. For example, a displacement or a voltage. The relationship between the values of the input and the output is called the response of that component with respect to a particular input. So if this is a physical system, this is a physical system. Okay. You look at it like that. Okay. So you see here is our box. So this is basically our measurement system. So the physical system, what it does, I'm just let me finish drawing this. So just giving you some examples. All of these are available in the book. It's a very nice one, actually. So these are your outputs, okay? And these are basically your desired inputs. and these are basically the modifying inputs, right? So this is a communication in which one component is communicating with the other component. These are basically, you can say, interfering ones, interfering inputs. Okay. So, for example, if you consider an experiment which uses a velocity transducer, say you are using a hot wire anemometer to measure. We will see what hot wire anemometer is later part in the course, to measure, say, velocity. This is what you want to do. Okay, so this measures once again the local velocity. Okay, local velocity. It is a nozzle from which there is a jet coming out. So this is the velocity of the jet, and you want to measure it at a particular point. Let's say this is the point where you are measuring the local velocity. You're basically parking. It's a hot wire anemometer is like a wire which you are parking over there. So the desired input is basically the flow velocity. So in this case, the input is your flow velocity, right? Okay. The draft of the air. Now this laboratory can have, ventilation system. There can be other types of air flows which are coming probably from all possible directions because of the ventilation system in the lab. So this distorts, these things distorts, okay, the jet velocity field. Okay, so this is like an interfering input. So if the ventilation or the cross flows are strong enough, it is going to do something to the jet velocity field. Now you can also have a change in room temperature, which can also act as a, so say delta T of the room can affect jet velocity. All right, so that can also affect the jet velocity. Now here the undesirable effect is that it modifies the response of the electronic circuit supplying the transducer, as well as causes deviations from the transducer's calibrated response, right? So you see, you have all these things interfering with your local velocity. So you have actually, electronics, which basically is, supplying the transducer. The response of the transducer, the response of the electronic circuit is actually varies because it will cause deviations from the transducer's calibrated response. So what people do is that sometimes you do something called filtering and compensation. Okay, how do you actually do it? Now, the undesirable inputs cause measurement errors and may produce an output even in the absence of the desired inputs. For example, when there is no velocity, just the ventilations can actually produce an input. Whereas we want to measure the jet. So the jet is not there. Even then, there is an undesirable input. Okay? And what the experimenter in this case should do, he should identify all these undesirable inputs and estimate their effects. So for example, if this ventilation, say if this velocity is say 100 meter per second, and this velocity, this distortion, let's call it distortion, say is of the order of say 0.1 meter per second. So naturally this effect, now we can consider it to be insignificant. But if this U distort produces a velocity of say 10 meter per second, which is roughly 10% of this, then it is significant. So this needs to be taken into consideration and applied as a correction. Okay? So you need to redesign a component that is sensitive to the undesirable inputs in a way that it is insensitive to them. For example, you can use materials with near zero thermal expansion coefficient, may eliminate the temperature sensitivity of a mechanical flow meter or a hot wire anemometer that has been calibrated to measure the flow in terms of displacement of some component. Okay? So you need to identify the components and design your experimental setup. Either you know them a priori so that you can subtract them out, or you need to design your experimental setup in such a way that your components are basically insensitive to these kind of things, like the example that I just gave. Okay, so the inputs and outputs may be constant within a time interval or fluctuating, because if you have a flow which say has, if you remember, it has a fluctuating component. So if there is a fluctuating component of the flow, that means the fluctuating component depends on time, then what we can do, say u is now a function of time. U is a function of time, say. So what we can do is that you can use so this is how the component probably varies. You see this is, say, the velocity profile with respect to time. What you can do over here, you can convert this to the frequency domain by using something called a Fourier transform. Fourier transform. Okay, so this converts the time domain and you get the frequency domain, right? So you get it to the frequency domain now. You can also do a Laplace transform or a wavelet transform. Now, a common way to reduce undesirable inputs is basically now the use of filters, which may be directly applied to an input or an output or one of the components. Okay, so that you remove. So what you do, you can apply filters. It's very useful to apply filters in the time domain. And what the filters do, it's remove undesirable inputs. So for example, if there is noise, if this, for example, this example that I gave, that there is a ventilation, right? And it is creating an undesirable input, that what you know kind of what is the frequency signature of that undesirable input. So what you can do is that next you can apply a filter to remove that effect completely. So there are filters which are called no pass filters. Okay, so what is a no pass filter? It removes all fluctuations. So if you think that your flow is steady and it basically removes all transient fluctuations and retains the steady state. Okay, so if you think that your flow is steady, then therefore you can apply a no pass filter, because in that case all other fluctuations are basically undesirable. Then you can have low pass filters, and this will be important when you do PIV and stuff like that. The low pass filters removes all fluctuations with frequency above a cutoff value. So therefore it removes fluctuations with frequency greater than some cutoff. Okay. Then of course you can go to high pass filters. The high pass filters removes frequencies, removes fluctuations with frequencies below a certain cutoff. So if your frequency is below a certain cutoff, it will remove those frequencies. Okay. Then of course you have the band pass filters. What does a band pass filter do? It removes all fluctuations except those with frequency within a certain band. So it's something like this. It keeps frequency, say, within F1 and F2, and anything which is less than F1 and greater than F2 are actually removed. Okay, so frequency less than F1 and frequency greater than F2 are removed. Okay, so it retains only so it removes all frequency except. Now the other part of this is a band reject filter, which is basically the opposite. So you basically have this. Okay, so this is F1 and F2. So if your frequency is less than F2 and less than F1, this is removed. Okay, so these are the different types of filters. What it allows is that if your undesirable input shows up at different frequency frequencies, then you can use a filter basically to decimate that component. So in terms of physical operations, now the filters, so if you go into this is a very important tool. In terms of the physical operation, the filters can be of different types. Okay, it can be electrical, electronic. Okay, applied to electric signals. Many of the inputs that you will see, if you try to measure the flow, for example, hot wire, it will give you a voltage or a current as your output, okay, as the component that is coming out of it. So most of the signals these days are electronic in nature. Okay, then you can have mechanical filters. Okay, designed to filter motion or forces. Like for example, shock absorbers is used to reduce vibrations. So that is also like a filter. And then you can have thermal filters. Now the thermal filters are designed to remove thermal fluctuations. It removes thermal fluctuation. Okay. And then, of course, you have electromagnetic filters. The electromagnetic filters are designed to remove the interfering effects of electric and magnetic field. Okay. Then you can have digital filters, okay, which applies to recorded signals. And you can have multipass filters, and this is something that we will use a lot. Actually do your PIV. It's applied to recorded signal. So you have a signal which is recorded, then you can apply these digital filters to do this. So another approach to reduce undesirable effects is compensation. By this, we understand that deliberate introduction of additional interfering or modifying the inputs, which may partly or entirely cancel the undesirable effects. Okay? For example, if you use compensation, I'll give you an example, which is the case of strain gauge. The strain gauge works on the principle of Wheatstone bridge. Okay? So in the case of strain gauge, the output is sensitive to ambient temperature fluctuations. So in what people do is that you put the strain gauge as one of the arms of a Wheatstone bridge. So this is your strain gauge. Because of its sensitivity, ambient temperature fluctuations, you attach it to a leg of a Wheatstone bridge. Okay? Strain gauge is routinely used in many applications. Okay? And connecting an identical strain gauge in the another leg. So if this is a strain gauge 1, you apply another strain gauge into another leg of the Wheatstone bridge. So this actually acts as a compensation. Okay? So you eliminate this effect by using a compensation, okay, by using the strain gauge thing. This makes the the circuit balanced. From that you can know that what is the fluctuation. So besides this compensation and filtering, analytical corrections could be also used to remove undesirable errors for such systems. Okay? This is routinely used. Okay? So the modes and functions of measurement systems. You look at it carefully. Okay, each component of a measurement system may operate in an analog mode, okay, or it can operate in a binary mode or in a hybrid mode. All right, so it may be passive or it may be active sensors, each class of the measurement system. So the main functions is like this. If you look at a sensor, the measurement system rather. The first part is the sensing. Okay. The sensing is the step in which the measured property excites a sensor. Measured property excites sensor. All right. And the output depends on the magnitude of that property. So this gives rise to an output which is proportional, okay, or which may not be linearly proportional. So let's put the term depends on the magnitude of the input of this property basically. Okay. So one example is, for example, if you put a thermometer in a bucket, this is a bucket and you put a thermometer over here, what happens is that it leads to an expansion of the liquid and it goes up to a certain value. More is the temperature, more is this rise. As a result of that, you can calculate. You can do the same thing by using a thermocouple. Okay, so this is a thermocouple, this is a thermometer. Okay, so the thermocouple also responds and gives rise to a voltage. Okay, so this is what happens, that it excites a sensor, the measured property, in this case temperature, excites a sensor, and the output depends on the magnitude of this property. Whatever is the temperature, E, that much is the voltage or that much is the rise in height, depending on what you are actually dealing with. So the first part is sensing. So the second part is what we call conversion and conditioning. Okay. So in this process, what we will do is that the components that transform the sensor's output to a form or amplitude that is more suitable for observations or processing. So we basically condition the signal that is coming out of the components that compose the sensor, okay, and we make it into something which is more suitable for processing. Then you have the transmission. Okay. Transmission is for transferring the signals from one component to the other. So one component to another component. So this is the transfer that happens, and then you actually present and storage. So this act in which the output is displayed, stored, and it can be also used for further analysis.